Today's topic is not particularly exciting, but it is important, especially for standard level. Questions about this kind of thing tend to show up in exams a lot. And a lot of you are going to want to also write IAs that deal in some way with data collection and data analysis. So it's going to be important for you to be aware of the different kinds of things that you can do with this. And in your IAs also, how to choose what to do depending on the situation that you are. So what data representations exists and to what kind of situations they are most appropriate. Because in exam questions, you don't really have to do that. They just ask you explicitly which one they want you to use. But we're going to begin by using this random looking data set. I just wrote down some numbers here and start from there, see what kinds of things that we can do with it. Now, when I ask people, look, here's a bunch of numbers, what do you want to do with them? Usually the first answer that I get is let's calculate the average, which means let's add them all up and divide by the number of numbers. And that is a good answer. Calculating the average is something important, relevant, and that we're going to do here at some point, but it's not the first thing that I want to do. What I want to do first is actually to count the numbers. There are 19 of them. And then I want to pick whichever number is in the middle of those 19 numbers. So if I get 9 numbers on a side, 9 numbers on the other side, that's 18. The 19th is going to be the number exactly in the middle. In our case, that is the number 3.4. And be careful that I've already brought you the numbers in increasing order, right? But that's not always in real life or in exam questions how your data is going to be. So when you're doing this, make sure to order the numbers first. For comparison, if you had calculated the average, the answer would have been 3.25, which is not that far off from 3.4. So both of these things are, in a sense, kind of trying to do the same thing, which is a way to find a number that is in the middle of all the numbers that you have. The difference is, what do we mean by middle? Because in this one is middle in terms of position of the numbers on the list. We've ordered all 19 of them and taken the 10th one, which is exactly in the middle. And when you do average and get 3.25, that is in the middle of the values. So like the 3.25 is here. And for example, that 1.8, which is really small, when it got added, it tried to pull this number this way. But the 4s, on the other hand, are pulling this number this way. So it's like values playing a little bit of tug of war here, trying to find the middle point of the values. But when we did this, we ordered the list and we found the middle point of the order of the positions of the numbers on the list. Both things are valid. Both things are different ways to try to find one number that best represents the middle of your data set. You just have to know that both of them exist and what they are called. This one is the median, but both of them, the average as well, are measures of central tendency. We're going to make a list here of different measures of central tendency. I'm going to hold off on putting the average on the list for a little bit though, because I want to make a lot of observations about median first. One of them is that we had 19 elements in our list, so it was easy to pick who was the one in the middle. But sometimes we will have 18 numbers, for example, which is an even number. So if I have 18, 9 on one side and 9 on the other side, there's nobody exactly in the middle. So here we have a much simpler example, but we do have 8 numbers, which is even. So if we want 4 numbers on one side and 4 numbers on the other side, who is the median? It wants to be the number in the middle, but there is no number exactly in the middle here. There is no value on the list that is exactly in the middle. That's okay. In this case, we're going to use the values, okay, not the positions. This is an exception. So the number that is in the middle between 6, 7 is 6.5, and that is the median of this data set. So here's that observation that you have to average the two numbers in the middle. Now, before moving on to that other measure of central tendency that we've already mentioned, I want to move instead to another kind of measure in which this time I'm not going to be trying to look for a number to represent the middle, but to represent what the numbers are doing around the middle. So if the middle is here, it's possible that all the numbers are very close to the middle. It's possible that they are spread out around the middle. So that is how I want to measure now. How spread out these numbers are. That's a different thing because you can be spread out around this middle or around this middle. So one thing doesn't replace the other. Both kinds of measure are important. In this example, our numbers are ranging from 1.8 all the way to 4. So that is how spread out they are. That is one way of measuring them, which is the range of the numbers. So this is called the measure of dispersion. The range is the first measure of dispersion on our list. There's going to be more, and it is just the size of the interval. So the maximum value minus the minimum value. In our example, the range is 4 minus 1.8, which is 2.2. The problem with range is that sometimes it will look artificially bigger than it is. So 2.2 is the whole space that all the values take, but if you look at the 1.8, it is very far away from the 2.5, which is the next number on the list. So if you would ignore the 1.8, the range would be 1.5 from 2.5 to 4, which is considerably smaller than 2.2. So the thing is that when you just look at range, you can be getting an illusion of more dispersion than there actually is in the data set. It is still a measure that people use, but by itself, it may not be enough. So let's look at the next one. The next one is that now we are going to look just as the smaller part of the list. These are 9 numbers, and we are going to again pick the median of the 9 numbers. So it's 4 to a side, 4 to a side, 1 in the middle. This is the median of these 9 numbers. To this, we are going to give the name Q1. And then we're going to do the same on the bottom half, get the median of these 9 numbers, which is 3.6. And to this, we are going to give the name Q3. The letter Q here is chosen because of the word quartile, okay? Quartile is supposed to refer to 1/4, dividing something into 4 parts, which is exactly what we're doing to our list here. We are dividing it into 4 parts, 1, 2, 3, 4. As an observation, if we were in the even amount of numbers case like before, if our median was not using the 6 or the 7, then the Q1 of this side would be of those 4 numbers, including the 6, okay? This is different from what happened here, where we did not include the median 3.4 when we were looking for Q1. But in this example, we do include the 6 when looking for the Q1 because 6 was not the median. And also because in this case, we're looking for Q1 as the median of 4 numbers. Again, we are going to use the average of the 2 middle values. So Q1 is 2.5. And over here, Q3 would be 10.5. So anyway, we're doing this because we think that extreme values, like the smallest and the biggest ones in the data set, they may be an illusion of a dispersion that is not actually there. Sometimes this is happening and sometimes this is not. Like the 1.8 really was artificially far away from the rest of the numbers. The 4 at the other end, not so much. There's 3 of them and it's really close to 3.9, 3.6. So it's something that sometimes happens and sometimes doesn't, but we always can take it into account anyway, because this other measure of central tendency that we're going to work with now is the range, but only the range of the middle. So we separated our list into 4 quarters, and now we're taking the 2 middle ones, which is 50% of the data, and we're going to look at the range of that. That's going to be called the Inter-Quartile Range because it is still a range, but it is between the quartiles. Here you go, that is the definition. And with that, I can already show you the first graphical representation of data, the first of a few that we're going to be doing. So this is going to be called the box and whiskers diagram. And I put this observation here that it is important to draw it to scale because this is something that we're not usually paying attention to. Like, for example, in geometry problems, often the exam question will come with a diagram and an observation diagram not to scale. Or in another context, when you are sketching the graph of a function, you're going to point out all of the relevant features of the function, but it is a sketch, not a drawing, so you're not going to be drawing it to scale. But in this specific case, you do want to draw it to scale, okay? So the box and whiskers diagram is going to use all of these things that we've mentioned so far. This is called a 5-number summary of the data set. It's the minimum value, Q1, median, Q3, and maximum value. Those are the 5 numbers that you're going to use to make a scale for your box and whiskers diagram. I have grid paper here, so let's put the 1.8 in the beginning and use 1 square for 0.1. Now the 5 number summary is on the grid to scale. Let's pick the 3 middle ones and close a box around it. That's where the box part of the name comes from. And we're trying to highlight it in the picture because we are focusing on the 50% in the middle of the data, right? So that the most extreme values to the left and to the right don't influence so much our perception of what the data set looks like. The rest we're going to connect as well, but we're going to connect with a line that doesn't attract as much attention as the box. These are the whiskers of the graph. And because of the way that the 5 number summary was chosen by splitting the data into 4 quarters, we can say that there's 25% of our numbers are here, 25% are here, 25%, and 25%. Now, there's a bunch of questions that people usually ask about this. The first one is about precision, because I had 19 numbers, so 25% of 19 is not an integer number, so what's going on here? And the answer to that question is that this doesn't really matter because 19 is a small number, but you can do this graph for larger data sets as well, right? Hundreds and hundreds of numbers. So this difference starts to get really small compared to the number of data points that you actually have. So yes, the 25% can be a little bit approximated. In some situations with small numbers, it's not going to be precisely 25%, but it doesn't really matter. And the best question that people ask here is, how come this 25% is so large and this 25% is much smaller? Shouldn't all 25% be the same? And that is a very good question because it highlights exactly the difference that I was talking about before. Are we looking at values or are we looking at positions? Are we looking at how large the values are or at how many of them there are? And this 25% is looking at how many, right? It's 25% of the data points regardless of what their values are. And what this thing is highlighting is exactly the dispersion. The 25% that looks wider is because those points are more spread out around that interval. In the small box that has the same amount of numbers as the wide whisker, that just means that those numbers are closer to each other. That's why they take up less space. And that is why it is important to draw this thing to scale so that we can see the thing that we want to see, which is how the dispersion is happening in different areas of the data set. In this one, for example, we can see that the numbers are more concentrated on the right side, on the larger numbers. The left side of the diagram is looking more spread out. And by the way, this has a name. We can say that this data set is skewed to the left or negatively skewed because the left side is the negative side, right? And the other question that people sometimes ask at this point is, don't we lose a bunch of information when we draw this graph? Because there is a wide space in which these 25% are, but I don't know exactly where they are. I'm talking as if they are spread out here, but maybe they're not. Maybe all of them are like right here, and the graph just doesn't show me that because of where the 1.8 is. It has taken the whisker necessarily over there, but I don't see anything else in the middle. And this is correct. This observation is correct. We do lose information when we turn a bunch of numbers into one graph that only shows 5 numbers. But the thing is that this is exactly what we want. When we look at information that is too detailed, it is not easy for our brain to pick up like general patterns. We have to take a step back sometimes to look at things more clearly. And when we take a step back, we lose information because we don't see as clearly. We lose the details, but we do start to see this general trend of concentration in some parts of the number line, of left skewness that we didn't really see by just looking at the list of numbers. So we lose information in order to gain information. That's how all of this stuff works. Even when you take the average of a data set and it's 3.25, you're also losing information. You're losing the information of what all the numbers were, and now you only know the average. But that is maybe more information, you know, around where the numbers are concentrated. So anyway, this was the box and whiskers diagram, our first graphical representation of data that we're going to be using. I'm going to keep it to the side here because I want to go back to this and continue on with our list of measures of central tendency and dispersion. But it's important for you to know that these two came first and side by side with each other because they go together, okay? We don't usually mix and match between the elements of this list. It's like median goes with range and IQR, and mean, which is the next one here, is going to go naturally with the measures of dispersion that we're going to put here. So anyway, mean is just the average of the numbers, right? And average is to add all the numbers on the list and divide by the number of numbers. I also like to point out here what is the symbol, the mathematical symbol that we're most often going to be used for mean, which is this. It's the Greek letter mu. But now we need to talk about what measures of dispersion are going to go together with this. But before we do that, I want to go on to the calculator and show you how to get these measures in the calculator, because median and IQR are really simple to do by hand. You just count the numbers and circle them. But mean is already annoying. It's adding a bunch of numbers, and even though that is something that is technically easy to do, if there are a lot of numbers, it's not something that you want to do. It's the kind of thing that technology is good at: simple, repetitive tasks. Okay, so the first thing that you need to do is to type the list of numbers into the calculator. And for that, you're going to click the Stat button. And the first option on the first menu is Edit. That brings you to a list. I've already typed the numbers here to save us time. Just so you know, in case you get to this screen and there's already a bunch of numbers on all the lists and you want a quick way to clean them, you go up until you're highlighting the title of the column, and then you click Clear and Enter, okay? So after you've put your data set on the list, you want to click on Stat again, but this time you're going to go to the second menu, which is Calc, and you're going to choose the first option here, which is 1var stats. Be careful because sometimes here the lists that he wants to use are not exactly the same as you want to use. In our case, we have only typed our numbers in this list called L1, so this is correct. But we're not using L2 for anything. So if this happens on its own, you just clear it, okay? Leave that blank because we're only using one list, not two. And then you go to Calculate. This screen is giving you a bunch of things at the same time. First of all, the mean is this first number here. I know that we talked about the symbol for mean being this, but the calculator is using X bar, so okay. The standard deviation, which is our measure of dispersion, is here as well. He is using sigma x. We are usually just going to call this sigma. And there are a bunch of things on the screen that we don't care about. You don't need to worry about that. Just be careful not to get the standard deviation mixed up with this other number here, Sx, which is kind of similar, kind of close, so people sometimes do get them mixed up. And if you keep scrolling down on this screen, there are a bunch of other things here as well. He's even doing the median for you, okay, so that can be useful. Of course, you still have to know how to do the median manually like we were just doing, but if it happens to be in a calculator question, then maybe you don't have to do that. It's faster to just let the calculator do it for you. Okay, so now that we've done that, let's look at what it means. And what I have written down here is a really vague sentence. Standard deviation is a measure of how far away from the mean the numbers are. So this points out the fact that it goes with mean, like I had already said. The symbol that is usually used for this is the Greek letter sigma, as we've also seen in the calculator. But this sentence is not really saying anything. It is a measure. What measure? How do you measure it? How do you calculate it? And in a sense, I am doing this intentionally because it is not something that the IB syllabus focuses on. This is really a calculator part. You need to know what it is, what it's for, and how to get it in the calculator. But this is not something that most people feel comfortable with, so I am going to go a little farther. So no matter how you write down this vague sentence, just make sure you avoid using the word average, because a lot of people have a tendency to do that, to say that the standard deviation is on average how far away things are from the mean, but that is not correct, okay? Do not use the word average. It's better to be vague than to be wrong. So before I tell you more about this, let me put another measure of dispersion on the list, which is also a really common measure of dispersion. This is called variance. And this one is the average of something. So I have put the word average here this time, but it's not the average of the distances. It is the average of the squares of the distances. Again, calculating this is not something that the IB focuses on, but that is a little bit more precise sentence. So we can turn that sequence of words into a sequence of symbols to write down a formula for variance. So it is an average, right? And we know from the left side here that average is add everybody and divide by the number of numbers. So let's divide by the number of numbers. Let's call that n. I think it's a reasonable letter. And we're going to average the squares of something. So something squared being added up here. Now follow along as I read each word into a symbol, okay? We did the word average, we did the word square. Now we're going to do the word distance. It's the square of the distances. How do we put distance? Is a subtraction, is a distance to the mean, and I've already said that the symbol for mean is this one. The distance from what to the mean? Well, from each number on the list, let's call them x, but not every one of them is x. You need a different x for each number because they are all different. And the way that we usually do that in symbols is to put a subscript. So it's going to be x1, x2, x3. This I letter is going to be going through 1, 2, 3, all the way until n, which is x19 in our example, right? And then we're going to take all these distances that are squared and we're going to add them all up for all of our numbers. I going from our very first number to the last one, which is n. So this is variance. I want to put a left side to this equation, but I forgot to tell you what the symbol for variance actually is. And that symbol is sigma squared. So you see that if you actually wanted to write down standard deviation, which is just sigma, it should be the square root of this other one. It should be the square root of the variance. This is correct, okay? This is the actual calculation to find standard deviation. Again, don't focus on this, especially if you're scared of it, because this is not something that the IB is focusing on. You can just use your calculator. What I really want you to do is, if you want to focus on this, I want you to not memorize it as a sequence of symbols devoid of meaning, because that is not how people who actually understand math do these things. The memorization is a lot different than just a sequence of symbols. We memorize the concepts, like the words, the sentences, what's written on the top of the page here. This is the kind of thing that we memorize, precise definitions of concepts. And then writing down formulas is just a matter of translating into symbols exactly in the way that I've just done with you right now. Now, I am going to take this away from here because I don't want you to focus on it. And instead, I want to just finish our list of measures of central tendency and dispersion before we can move on to doing more graphical representations of data. And I think that the only thing missing from the list really is a measure of central tendency. You've probably heard of this. There's three of them, right? Mean, mode, median, and we haven't talked about mode yet, so let's put it on the list. Mode is the number that appears most frequently. We're going to go back to the list of numbers and figure out who that number is. But I should also tell you that mode is the most irrelevant of the measures of central tendency, okay? So what's going on here? We have 3 3s, 2 3.4s, 2 3.5s, 2 3.6s, and 3 4s. Okay, so that is also a good observation about mode. There can be more than one mode if there is a tie like this. Three of one of them and three of the other one. This data set has two modes. There's even a fancy word for it. You can say that it is bimodal. And the other observation that I like to make about this is that it kind of annoys me that mode belongs on the list of measures of central tendency. Because remember, we talked about how mean and median, each in their own ways, were trying to find the central value of the data set. One of them was looking at the middle of the values, the other one was looking at the middle of the positions. But mode is not really looking at the middle of anything. It's just looking at high repetition. And as we can see, sometimes repetition occurs close to the middle, but not always. In this case, we have 3 4s, which is the very highest number on our list. So that would be my second observation here. Mode is not really central. Okay, so let's go ahead and make more graphical representations now. I want to make a frequency diagram, a diagram that represents how frequently these numbers appear in my data set. And in order to do that, I'm going to first turn my original list into a frequency list. Oh, frequency table is how we usually call that. So it's going to be a table with 2 columns. First column is going to be the value, and the second column is going to be the frequency. We are going to start with 1.8, which is the first value, and there's only one of him. The same goes for 2.5, 6, 7. But then when we get to the next value, which is 3, suddenly we have 3 of them. And then only one 3.1, one 3.2, but then we're going to have 2 of each for 3.4, 5, and 6. Finally, one of 3.9, and for the number 4, we have 3 copies of that as well. We're going to need that frequency table in order to make our frequency diagram, so let's leave it on the side here. And frequency diagram should also be done to scale. I am going to line it up with the box and whiskers that is above it on the page. I'm going to use the same scale. So for 1.8, I have one of these things. So I'm going to make a little bar that is 1 square tall. Also for 2.5, 6, and 7. And notice that it is 1 square tall because the frequency is 1. But I don't want to paint the whole square because I want to leave some space between the bars, okay? This is how the frequency diagram is supposed to look like. So for the 3 bar, it's going to be taller. It is 3 squares tall. Then you have 2 short ones, and then there's going to be 4, 5, 6 with 2, and finally 4 with also 3 frequency. So supposedly you should be able to see when you line them up like this how both diagrams are showing the same information, but they are showing them in kind of different ways. The thing that we talked about the box and whiskers earlier, how we are losing some information, we don't really know exactly where within the whisker the numbers are. The frequency diagram doesn't have that problem. We can clearly see that this is where the numbers are. But it has the opposite problem, okay? No representation is going to be perfect. It's just what is more appropriate for what you are trying to see. So yes, the frequency diagram has more detail, but if you're trying to think about quartiles and where is the middle 50%, this is more difficult to see in the frequency diagram. Not so much in this one because all the bars are kind of the same height, but when it starts fluctuating some more, then this kind of thing becomes more difficult to see in the frequency diagram because you would have to count. And when you're looking at a box and whiskers, the counting has already been done when we were looking for the 5-number summary. But there are situations in which the long whisker in the box and whiskers is hiding too much information. And I think this might be one of them because there's all of this empty space between 1.8 and 2.5 that we've been mentioning since the beginning. So there is a standard way to handle these things. We want to let the different quartiles have the sizes that they have in order to represent concentration and dispersion. But if a whisker is too long, then sometimes it doesn't represent that. It just represents that there is one number who is falling away from the pattern, like this 1.8. So there is such a thing as a whisker being too long there is such a thing as a number being too far away from the middle 50%. And there are very specific, precise criteria that we should use to determine where is this too far away. The word for that is outliers. Those are the numbers that are too far away from the box part of the box and whiskers diagram. And I'm going to show you first how to decide who is and who isn't an outlier, and then what to do about them in the diagram itself. First of all, you're going to consider the box. Let's look at how wide is the box. That is basically the IQR, right? The distance between Q1 and Q3, which in this case is 0.6. So that is the first calculation that you're going to make. IQR is equal to 3.6 minus 3, which is equal to 0.6. And then here's the thing. You're going to basically use the box as a measure of how far away from the box the numbers are allowed to be. So let's make a copy of this box, and then we're going to move it to the sides. Look, to the right side, there is no problem because I've put an extra box and that is already covering all of the numbers on my list. So there are no outliers there. Now, if I put the box on the left side, that's different because the 1.8 is clearly far away from that, and there may be others that we're not focusing on because they're in the middle of the whisker. And that's not even the whole thing. We are not going to use the length of one box as this criteria for how far we can go. We're going to allow it to go a little bit farther away. Like we're going to use a box and a half as a measure of how far we're allowed to go, like a slightly bigger box. Well, not slightly, like 50% bigger box. So in order to get there numerically, what we have to do is to take the IQR and multiply that by 1.5. That is increasing 50%. So 0.6 times 1.5 is equal to 0.9. And again, numerically, the way to put it in the graph, remember where the bigger box used to be. It was right here, and the width of the bigger box was 0.9. That means that starting at 3, how far to the left was it going? 2.1, right? That is how you put something 0.9 to the left of 3, is that you subtract it. And 2.1 now, because it has been arbitrarily determined to be the barrier between what is not too far away and what is too far away. This is completely arbitrary. Somebody just decided it and you are required to know it. But so all the numbers that are less than 2.1 in this example are outliers, like the 2.8, and everybody that is bigger than 2.1 is not an outlier, like the 2.5 that is the next number on our list. So here's what we're going to do about it in terms of the diagram itself. We are not going to let the whisker go all the way to the outlier. We are going to delete part of the whisker. We are still going to keep the outlier in the picture because it exists. It's part of the data set, but we're just going to represent it with a dot. And we are not going to put this 2.1 here because it is a barrier, but it is not a point in the data set. Our data set is going straight from 1.8 to 2.5. So the next number that we want to see is not 2.1, it is 2.5. 2.5 is here. So that is how far the whisker is going to go, okay? Not 1.8 and not 2.1. The whisker goes all the way to the last number that is not an outlier. So I've written down that observation here right now. And another interesting thing that people sometimes ask is, what about the 25%? Where did it go? I think we should say that the 25% goes here on the remaining whisker, because now it's not exactly 25% because it is minus 1 point. But then again, we've already talked about this before. The 25% was approximate anyway, because 19 was not divisible by 4 and all of that. And it doesn't really matter when the data set is larger. You're not usually going to get a big percentage of data points being outliers. You're going to get 2 or 3. So that's not really going to impact on the 25%. And now that we've made that change, it aligns even better with the frequency diagram, right? There's an isolated point at 1.8, and then everything else we can see kind of similar. So I wanted to show you also that exam questions sometimes already give us the information as a frequency table. In fact, that is quite common. And that if they ask you for things like mean and standard deviation in that kind of situation, you can also use the calculator for those answers, but then you don't have to like put 333 just because you see that the frequency is 3. You can type it in the calculator as a frequency table as well. Let me show you how to do that. Okay, so for the frequency list, we are going to get into the stat edit again. And this time, of course, we are going to need 2 columns for our frequency list, okay? Let's try to reuse what we already have here. 1.8 is appearing one time, 2.5 is just one time, same for 2.6 and 2.7. But now, instead of 333, we want to say that the 3 is going to appear 3 times, but because we have already typed this list this way, we have to remove the other 2 3s. A lot of people get the clear button that we were talking about before confused with the delete button. But right here, if you just want to delete one value out of the list, it's the delete button and not the clear button, okay? They do different things. So 3.1 frequency 1, 3.2 frequency 1, 3.4 is frequency 2, and I am going to delete the second one. I'm also deleting one of the 3.5s because that has frequency 2 as well, and frequency 2 for the 3.6. Let's delete this one. Frequency 1 for 3.9, frequency 3 for the 4s. Let's delete the other 2 4s. Okay, so now what I have here is a frequency table with the values typed in L1 and the frequencies typed in L2. So that this time when I go into the stat calc 1 var stats, same exact screen, but now I do want to use a frequency list, and that is L2. Let me show you how to put that here. Sometimes we don't see it when we don't know what we're looking for, but the L2 is right here. Look, it is a blue thingy above the button for the number 2. So you're just going to click it there by second and 2. You can also use this in case you want to reach L3, L4. Sometimes we type multiple lists. And then anyway, just calculate. And of course, the numbers that we are seeing here are the same numbers as we saw before because we just calculated the same thing in a different way. And the other interesting thing about frequency tables is that sometimes they come with a third column, which is called cumulative frequency. And it's just not how many of that specific number we have, but how many until that number we have. So we have one of 1.8 and one of 2.5. So until 2.5, we have 2, which is this one and this one. And then we just keep going down the list and adding the frequencies in order to make the cumulative frequencies, right? Adding is accumulating. Sometimes they ask you to do this. Sometimes they give this to you as part of the problem statement. One of the things that's interesting is that when you get to the end of the cumulative frequency, you get the total amount of points that you had. In this case, it's 19. I don't think it's very relevant in this example because there isn't so much repetition. But if you get another example in which the list is bigger and a lot of the values are repeated, this makes it a little bit easier to find the 5-number summary, the median, and the Q1, Q3, because you don't need to put the whole list with all of the repetitions to count the numbers. Instead, you just know that the total is 19. So for the median, there's going to be 9 on the left, and then 1, and then 9 on the right side. So you're looking for that 10th number, the one that makes the total reach 10. So you can look at the cumulative frequency and see, well, here it was only 9, so 10 is on the next line, which means that 3.4 was the median. If you want to separate this 9 in order to get the Q1 as well, you're going to get 4 and then 1 and then 4. That's going to be the Q1 is the 5th number on the list. So you go, well, here I only had 4, so the 5th one is in this line. So that means that Q1 is 3. So this is not a new concept. It's just median and Q1 and Q3, but I'm showing you a different kind of situation and how you can apply those concepts in the case of a cumulative frequency table. It can be a little bit more convenient if that is what you have. So the next thing that I want to talk about, keeping this example in mind as a motivation for the things we're talking about, is that don't you find it a little bit suspicious that the modes that we have, the two modes, were exactly 3 and 4? They were very round numbers. Okay, so I didn't tell you where these numbers came from, but they were things that I was measuring with my students in class, some papers that they had folded, and they were measuring them with a ruler. So those were centimeters, right? The smallest one was 1.8 centimeters. There were things that were up to 4 centimeters. And I think that the modes were 3 and 4 because not all the students were very precise with the millimeters on the ruler. They just looked at it and said, oh, that's 3, which is fair. It's a natural thing to do. And it is an intrinsic problem with what we were doing because the numbers that we wanted to put on the list were not these perfect looking numbers with just one decimal place. They were numbers that were measured on a length of paper that could have been any number. It could have been 3.27222 centimeters long. We just wouldn't really know it because of the precision that the ruler has. It only goes down to millimeters. But that is bringing me to talk to you about a very important distinction in data, which is discrete data versus continuous data. So the first analogy that you can make to explain this distinction is that continuous is the real number line and discrete is the integers. So the number line, you draw it horizontally like this. Any point in here can be a number on the real line. It doesn't have a limitation on how many digits it can have. It can even have infinitely many digits. It can be an irrational number. There are no gaps between what the numbers can be. If you keep zooming in, you can put one in between the numbers that are already there. So that's why I draw it horizontally, because it's continuous. The integers, on the other hand, are very precisely positioned. You have 1, you have 2, you have 3. So if that's what you're doing, if that's the kind of number that is in your data set, even though you can see that there are numbers between 2 and 3, you're not going to be allowed to put 2.5 or 2.4 in your data set. So there is this gap between numbers that are allowed in the data set. But it's a little tricky to say that it's the integers because the numbers that we were looking at were not integers. They were 1.8, 2.5. That's an analogy, okay? Even though these have one decimal place, so they're not integers, there is still a gap because I wasn't allowing 2.53, for example, as a number in my data set. And again, that is because there is no 2.53 in the ruler. So you shouldn't use a ruler like that. You should only use the precision that it goes to. But here's where it gets confusing because the other analogy to make between discrete and continuous is that discrete are things that you count, such as how many cats do you have in your house. I hope you do not have 0.73 cats. And continuous are things that you measure, like lengths, like time, like weight. You use different instruments for measuring things, but the answer can technically be any number in the real line. And yet, I've just told you that the problem with our continuous data was precisely the fact that we were measuring it, right? There is a problem, there is a discrete problem in our measuring instrument for continuous lengths. That is not a problem that you are going to get around. This problem always exists. What you can do is learn how to treat continuous data. One of the things that you can do is exactly what we've been doing so far. We have been treating continuous data as if it was discrete, because all of the things that I've showed you so far in this video are things to do with discrete data. And I'm going to talk to you about some things that we could have done differently, some things that we can do to treat continuous data specifically. So the first difference that I want to point out is here when we were in the measures of central tendency and dispersion. When we were talking about mode, I want to make one more observation about mode, which is exactly this. It only makes sense for discrete data. You shouldn't talk about mode on continuous data. And the reason for that is the mode talks about the frequency, how many times the same number appears. But if you're doing continuous data for real, then the same number is not going to appear twice. Everybody's just going to have the same frequency of 1, and then the mode becomes something that is really irrelevant. So in our data set, even though it was originally continuous, it was a length, it was something that we were measuring. If we have the number 3.4 appearing exactly the same, 3.4 and 3.4 twice on that list, it doesn't mean that the lengths were the same. Maybe one of them was 3.39 and the other one was 3.41. They were different. They are just being treated as though they were the same because they've been rounded. That's in the treating continuous data as discrete that we have been doing. And along the same lines, the other thing that is not going to make sense for continuous data is the frequency table, for the same reason, because you are not going to get three numbers being exactly 3 or two numbers being exactly 3.4. That's just not going to happen. And the frequency table is just going to be 1, 1, 1, 1, 1, 1, 1, which makes it irrelevant, as well as the frequency diagram, in which every bar would have just a height of 1. The other things that I've mentioned basically remain the same regardless of discrete or continuous, okay? But what you want to do instead of a frequency table here is that you are going to group the continuous data into categories. In a sense, that was what we were doing, because if we had the 3.2, 3.3, 3.4, 3.5. So when we round a number to 3.4, what we were saying is that it had originally been somewhere in this interval from 3.35 to 3.45. So that would be a category. And that's another category right next to it right here. So when we round the numbers, we are grouping the continuous numbers into categories, but that doesn't need to be done by rounding. The categories don't need to be that narrow. For our data set, I think that it would make sense to group them into spaces of half a centimeter, like from 1 to 1.5. Well, there's nobody there, but from 1.5 to 2, from 2 to 2.5, and so on. Notice how for all of my categories, the number that ends one of them is the same number that begins the next one. Okay, so I am actually covering the whole range of data. And also that the same number is not appearing with an equality on both lines. In one of the lines, it is a less than, and then in the other line, it's a less or equal. I have chosen to put all of the less or equals on the left side of the interval, but it doesn't have to be that way. That's a choice. And in practice, it's not really going to matter anyway, because the same feature of continuous numbers that makes it so that there are no ties in general also makes it so that no number is really round. So when you get a 3, for example, you don't really have to decide whether to include it in this category or that one, because it's either going to be 2.999 and then it goes in one of them, or 3.000 something and then it goes into the other category. These are edge cases that are not really worth our time. But the point is that this is like a frequency table. We put frequency here and we just count how many are in each category. So we have 1 here, nobody in this category, okay, because the 2.5 is actually going to count for the next category. So 3 here, 7, 5, and 3. I told you that the concept of mode doesn't make sense in continuous data because there are no repetitions, right? But when you look at a frequency table like this, you can see that one of the lines has a higher frequency than the other lines. We just can't call that a mode because it's not one number being repeated. It's 7 different numbers that have been grouped together, and no other category has more than 7. So that is not exactly a mode, but it's called a modal class, which is also something that they sometimes ask you to identify. So I just wanted you to know the word. This looks very similar to what the other frequency table looked like. It's just been grouped more because that is what we are doing. We are grouping the data into categories. And as a consequence of having grouped more, our frequencies got higher. And now we have a smaller number of bars that we are going to draw. But we are going to draw something that looks similar to the frequency diagram. It is called a histogram. It is a kind of data graph that is used for continuous variables specifically. And one of the differences is that the labels that we're going to put on the horizontal are not the names of the bars. They are the endpoints of the intervals. The bar is going to be between the numbers, not on the numbers like the frequency diagram was. So between 1.5 and 2, we have a histogram with a bar of height 1. Between 2 and 2.5, we have nothing. So now between 2.5 and 3, there are 3 squares of height. The other one is between 3 and 3.5, we have 7, and so on. The other difference that you can observe between this and the frequency diagram is that this time the bars are touching each other, not leaving that space in between the bars that I insisted on leaving the other time. And that is because these intervals are touching. One of them ends at 2.5 and the other one starts at 2.5. Like we mentioned here, there are no gaps in continuous data. But in discrete data, there are gaps, which is why these bars were not touching, because there were no numbers between 2.5 and 2.6. Like the 2.53 cannot be there, and that's what justifies this gap in the bars. Cumulative frequency is also something that plays a similar role in continuous data. So this would be 1. And on the second line, I don't have anybody new, so it's still 1. The next one, 1 plus 3 is 4, and so on. But the thing is that usually these will be larger frequencies, okay? Larger amount of numbers in the data. The example that we are working with is somewhat artificial because it's only 19 and we still remember what all the numbers are. We still have a list of them. But that is not usually the situation. Usually the numbers have been grouped, and one of the reasons, yes, is that they're continuous, but the other reason is that there were a lot of them. So usually we don't have that more detailed information about what the numbers are. All that we have is this grouped frequency table. And from here, we may still want to calculate our measures of central tendency and dispersion, like mean and standard deviation, for example. But there is a problem, because how do you add everybody and divide by the amount when you don't have everybody to add? And the thing that you're supposed to do here, what you're expected to do if an exam question asks you about this kind of thing, is that for each one of the intervals of grouped data, you're going to pretend that everybody that is between 1.5 and 2 is exactly 1.75. That is not an unreasonable assumption. This is what's going to minimize your error in the absence of more information, because it's the number exactly in the middle. So if you guess too high, they might have been smaller. If you do the opposite, you risk being wrong the other way. But if you guess in the middle, how far away the numbers are able to be from you is only half of the interval. So that's the smallest. So you're going to do that for all of the intervals. And these values are called the mid-interval values. The name is not really surprising. And when you want to calculate mean and standard deviation, you're still going to do it in the calculator like I showed you before. But don't attempt to type intervals into the lists in the calculator. That is not how this works. Instead, you are going to type it as a frequency table, like I've already showed you, with these values and these frequencies. This is how you estimate mean and standard deviation from grouped continuous data. Everything that you do with this kind of data has to be an estimate, right? Because you don't have all of the information. But let me show you, I think, the last type of graph that I have to show you, which is going to be the cumulative frequency graph. Like all of the others, it's going to have values on the horizontal axis and frequencies on the vertical axis. It is the first one that explicitly draws a vertical axis, but the other ones were already putting frequency on the vertical and values on the horizontal. So that's not going to change. So I've made my vertical axis going up to 19 because that's how many I have. And on the horizontal, I want to go up to 4.5. Now to build this graph, we are going to look at the values and the cumulative frequency. So the first point that I'm going to put in the graph is 1.5 and 0, because before 1.5, there was nobody. So here's that point, 1.5 and 0. After that, at the end of this interval, I already had 1, so the next point is 2, 1. I don't know exactly in which part of this interval between 1.5 and 2 the first data point appeared, but it was somewhere in here. So as we go through that interval, we go up from 0 to 1. We're going to stay at 1 for until 2.5. That is a little bit unusual for a frequency diagram, but that's okay. That's what happened in this one. So the next point is 3 and 4. And then I've put all the other points here. Next, we need to connect these dots. Some people like connecting them by straight line segments, and other people like doing like a little curvy thing going through all of them, and that's a visual thing. There's no precision in this graph, okay? The reason why I'm picking the curvy version is because they don't often ask you to draw this, but they do often give you exam questions in which they show you one of these things and they ask you to do things with them. And when they do that, they tend to connect the dots as a curve, okay? In fact, you're not even going to see the dots in most cases. It's just a curve. One of the very common things for them to ask you to do with this kind of graph is to estimate the median, and then the Q1, the Q3, then do a box and whiskers graph with that information. Median is when you look at the half point of the list. So the list still has 19 elements. Half of 19 is 9.5. So you're going to look at 9.5 here vertically. Yes, because 19 is odd. When we were doing this in a different way, we were looking at the 10th value and not the 9.5 value. But that's not a consideration that we're going to have in this kind of situation, because usually this kind of graph is not done for 19 values. Usually it's hundreds. So we are already at that point where it doesn't really matter. 9.5, 10, it's going to be the same value anyway. So then we want to find out what value is in position 9.5. So remember that the 9.5 is positions, it's frequency, and the values are on the horizontal. So yes, we want to know what the value is. That's going to be our answer. And in this case, it's looking like 3.4 approximately. But a lot of students tend to be confused and pick the midpoint of this interval instead. That's the middle of the values. That is not where we go looking for median. That would have been equivalent to looking for median in this list by saying, well, the midpoint between 1.8 and 4 is 2.9, so the median is 2.9. That is not how we did it here. We did not consider midpoint of the values, so we are not going to do it here either. We are considering the midpoint of the frequency. Find the midpoint, and then we find the curve, and then from the curve we find the value. That's going to be the same for Q1. Q1 should be half of 9.5, right? So it is kind of around here. So we go look for the value in that position. Our Q1 looks like 3.1 in this case. Q3 is looking like 3.8. Now the first value was 1.5. The last value was 4.5. So if you want, you can draw a box and whiskers diagram right here, aligned with the scale that you already have in the picture. That is a very common question in exams. There's just one more vocabulary word that I would like to mention in this context, which is percentiles. A lot of times in the cumulative frequency diagrams, they're not just going to ask for the median or for one of the quartiles, but percentiles, which is something very similar, except instead of 25%, 50%, and 75%, which are the Q1, median, and Q3, it can be any percentage. So for example, if they ask for the 90th percentile, it is after 90% of the numbers have already passed. In this example, 10% of 19 is almost 2, so it would be somewhere around here. The 90th percentile of this data set would be something like 4.2. Right, so those were all the measures, those were all the graphs. I have tried to comment upon usual types of questions and usual mistakes that people make. I guess the only other thing that I would still like to mention is that even though the distinction between discrete and continuous is clear in theory, in practice, this is a lot more fuzzy, as we've already seen an example where we did a whole lot of things with continuous data by treating it as if it was discrete. And I wanted to mention, because this example didn't show it, that the other direction is also very possible and very common. Okay, you can, in a lot of situations, choose to treat discrete data as if it were continuous. This is going to make the most sense in situations in which two things. First, the amount of numbers on your list is very big. And second, the size of the numbers on your list is very big. For example, when you're dealing with amounts of money, money is discrete, whether you choose to break it up into dollars or into cents, which is a smaller gap, it is still a gap. So they are technically discrete numbers, but you still want to do things like grouping and considering similar values as if they were the same value, because there's just so much variation within the range of values of money that you are going to be studying. There is so much variation because the numbers are large and the gaps are small, that it almost looks like a continuous line. So yes, you should absolutely group values to make a frequency table with higher bars. In this case, you should totally draw a histogram for this kind of situation, even though technically histograms are for continuous data. Discrete data has gaps. It doesn't matter. If your data is discrete but you're treating it as continuous for those kinds of reasons, then you do a histogram. And that's it. I'm not going to go through exam questions this time, but I hope that when you do that, you recognize the types of questions and you don't fall for the common mistakes in a lot of these tiny little details that we've been mentioning for the past hour.